So we had 6.89% for 0 and 8.6%.
I think it was 4. It is
4. 6.4%. So when we're looking at these, you know, obviously 6.89% is going to have closer agreement, right? But still, is that very close agreement? No. And so when you look at these, they kind of look the same. 7, 8%, 9%. You know, and so we worry about that sometimes, you know, in assigning this. Now, if one was like, you know, 1.89 versus 8.64, or 0.89, you know, versus 8.64, then it's a clear, you know, clear cut. But when we have a situation like this, we always have to worry about, you know, random errors. We're only taking 3 data points, you know, and if there's random fluctuations in those data points, then those could skew our results or bias our results, you know, depending on that. And so the best thing is to collect more data. You know, the more data we have, the more we can average out random error. Correct? Yeah. And so if we were to go with this, then this reaction should be what order? 0 order, right? And that's the case. But a 6.84% still doesn't leave you a lot of comfort that that's really linear, you know? I mean, that's getting close. Okay, if you were to round it up to 1 sig fig, it'd be 10% error. And so what should we do in a case like that? Well, probably we should look at some more data, you know, to see, is this really this case? And then see which one would give us better agreement. And so we might as well, should we finish this up today or tomorrow? Let's finish this up tomorrow. You know, it's something to think about. Today I want to talk about this. You guys recognize these reactions, right? And so let's say I had a reaction like this. Let's say A plus 2B yields G, something like that, plus 8. And you saw this. We monitor the concentration of A over time, and you see it decay like this. Okay, just looking at the data, what would you say the order is? Can you just eyeball the data and tell me what order that is?
First order?
Yeah, first order, right? This looks like a first order rate, first order decay. And so the question comes up, is this first order with respect to the concentration of A? Make sure that's recording. Is this first order with respect to A, WRT? What would your answer be? Multiple choice. True or false? Yes or no? Actually, yes or no. Is this first order with respect to A? Yes or no? Yes. You'd have a 50% chance of getting it right, maybe. Maybe better. Yes? Yes? No or maybe? Just decrease your odds. Yes, no, or maybe?
Not enough information.
Or not enough information. That's a favorite of mine. Not enough information. Yes? No? Not enough information. You'll see that. What do you think? How many people say yes? Why do you say yes? Hmm?
The graph has A on the y-axis. Yeah, that's what I was thinking. I mean, what else could it be?
Well, how do you know it's first order? How about that, Jason?
Because it's not linear.
It's not linear.
It doesn't look like second order because it's not turning into a quarter.
Yeah, okay. So you're looking at the half-life. Right, the half-life appears to stay constant. So it looks first order. And it's A, and so how many people say no? How many people pick C? Not enough information. Omar, you pick C? Yeah? Anybody else pick C? You pick C? Yeah. The correct answer is C. Not enough information. But you know, why is there not enough information? What? Son? There's no scale? All right, here's... It looks perfectly first order. Half-life is constant.
There might be arrow to make it.
Well, you only have three choices for us. It's either got to be 0, first, or second. We haven't talked about any other order.
What the concentration drops, the scale of concentration drops.
Oh, this is linear. And so this would be let's say this is A0, you know. This would be 1/2 A0. This would be 1/4 A0. This would be 1/8 A0. We could look at the slope or the rate too. You know, this would be 1/2 the initial rate, 1/4 the initial rate, 1/8 the initial rate for the slope. So this looks perfectly first order. So why isn't it first order?
So this is experimental, right? So there might be experimental arrow to make it perfectly the first order.
Experimental error, yeah. Let me ask you another question. Is this first order maybe I shouldn't ask that question. Let me not ask that question just yet. The reason why is because, you know, I didn't tell you something before. When we were looking at these graphs, I didn't tell you that all the graphs were valid when we had one reactant decomposed into product. And so just a simple decomposition like this. But what happens if you have two reactants here? Because, you know, if A gets cut in half, what's going to happen to B? If A gets cut in half, B is going to be cut in... Well, if A gets cut in half, B gets cut by twice as much as A, right? And so, well, if B's getting cut, then is that going to have an impact on the rate? Yes. And so what we see here is this. This shows the reaction to be first order overall. And so when we have multiple reactants, it complicates things. Because what can happen is it could be, let's say, first order in A and 0 order in B. Then this would be true. But it could also be 0 order in A and first order in B. If it's first order in B, then as B gets cut in half, the reaction is going to slow by half, right? And if the reaction slows by half because of B, then we aren't going to consume A as fast, even though there's no dependence on A. And so B is going to dictate the speed of the reaction. Does that make sense? And so we have to look at the impact of B. And so the reason there's not enough info is because we don't know how B influences the rate of reaction. We don't know how the concentration of B influences the rate of reaction. And we need to know that.
How would we know? Would that information be like given?
Yeah, how do we know that? Well, I'll talk about that right now. How would we figure it out?
So does the graph not actually look like that for A?
The graph looks like that for A. The graph looks like that, even though it might not be first order in A. The graph is going to look like that for B too. Both A and B are going to look the same. And so the reason is this. If I had something like A plus 2B goes to G plus H, then the rate is going to be influenced by the changes in concentration of A and the changes in concentration of B. Both of these will impact the rate. And generically, we just write it like this. Ka, the concentration of A, times B, just the reactant concentrations here. So for example, if you double the concentration of B, you expect the reaction to speed up, perhaps, right? But what happens if you double both the concentration of A and double the concentration of B? You know, and so we got to figure out what the influence of these are. And what the influence is the order. And so M is the order with respect to A. Boy, it's hot in here. N is the order with respect to B. If we had more reactants, we'd have more orders. These may or may not be the same as the coefficients. In general, the rate is not necessarily equal to K, A to the little a, B to the little b. Now sometimes it's equal to that, sometimes it's not equal to that. And so the coefficients might impact it, might not appear to impact it here. And so how do we figure out what's happening here? And so let's take a look at some examples of what different scenarios might be. An example, let's say it's zero order in A and first order for B. That means overall it's going to look like this. The rate is equal to K, A to the 0, B to the first. And overall, what's the order? Overall, this is first order. And so what would a plot of A look like? And what would a plot of B look like? Well, a plot of B, that should be easy to see. A plot of B is going to be B versus time. It's first order in B. So we cut the concentration in half. It takes this long. We do it again. It takes the same amount of time. And so it looks like a nice first order decay in B, correct? And so this is what a plot of B would look like. What would a plot of A look like? Would a plot of A be a straight line? Because it's zero order. A zero order decay should be linear. Right? A straight line. Now, the chemical reaction, you're having these collisions and things are being consumed stoichiometrically. And so for every A that's consumed, there are two B that are consumed. Is this possible, stoichiometrically, to have A being consumed linearly and B being consumed exponentially? It's impossible. And so what's going to happen is this. Even though the A has no impact on the rate, this is going to look not like this. This has got to look like this. It's being consumed at half the rate. So every one here, we're going to get some kind of curve like this. Does that make sense? And so it's not being consumed linearly. It's being consumed exponentially. It has to be, because B is being consumed exponentially. So how do you figure out, how do you figure out what the order is when we have multiple reactants? Okay. And so let's take a look at two ways of doing that. Let's take another reaction. Let's say we have 2A plus B plus C yields product, whatever the products might be. And we want to figure out what is the order with respect to each of these, so that we can figure out what happens to the reaction. So interestingly here, actually, if we go back to this one, let me just write this here. If the rate are equal to Ka B to the first, A to the 0, what happens if I double the concentration of A? If I double the concentration of A, does anything happen to the rate? No, because there's no dependence on A. A to the 0th is just 1. If I double the concentration of B, will something happen to the rate? Yeah, the rate should double. And so we want to know what the individual orders are so that we can see, how things vary. And so here, the rate law for this, the rate is equal to K, A to the M, B to the N, and C to the O. And so we need to figure out what M, N, and O are. And so if we were to graph the data, what we're going to observe is the overall order. The overall order is M plus N plus O. We'll see that as the result of the curve, right? Depending on that. And so there are two ways to determine the individual orders. The first way to determine it is to make it pseudo M order. We can make it pseudo M order, this reaction, rather than N plus O order by doing this. Use high concentration of B and C so that the final concentration of B is about the same as the initial concentration of B. And the final concentration of C is about the same as the initial. And so, in other words, we have so much B and so much C that they're barely touched. If they're barely touched, then does the concentration change during the course of the reaction? No, if the concentration is so high, let's say you make it 18 molar and you're barely touching it, and so at the beginning of the reaction it's 18 molar, at the end of the reaction it's 17.999 molar, did the concentration change significantly? No. And so what that does is it does this. The rate is equal to K times A to the M, B to the N, C to the O. And then since B and C don't change much, these are fairly constant. And so if they're constant enough, then we'll combine the two constants, the rate constant, K. We're going to call this K prime now. And now it's going to be A to the M. And so in other words, K prime is K times B to the N, C to the O. So does that make sense? And so these concentrations are high. The only thing that is changing is the concentration of A. As the reaction proceeds, A gets consumed in half. 3/4 of A is consumed, etc. And so we're consuming significant quantities of A. As we're consuming significant quantities of A, then we're going to see clearly that a chart of A versus time reflects only the dependence on A. So now if I were to ask you this, we plot A versus time. Is this first order in A with respect to A? Given that I made B and C highly concentrated. I'll just add that here. With B and C very large. So is this first order with respect to A? Yes. The answer is yes. We can easily see because that's the only thing that's changing. By the time I get here, B and C haven't changed at all, really. By the time I get here, the only thing that's changed is A. By the end of this reaction, when I decide to stop it, B and C haven't really changed much from the beginning. So if B and C's concentration doesn't change, then that's not going to have any impact on slowing the rate down, right? Does this make sense? All right, so now we can determine M. M must equal 1. Now, what about N and O? Have we answered that yet? No, how can we answer what N is? Yeah, all we do is we repeat this and make it pseudo O order. How do you make it pseudo order? You just make sure that the concentration of A and the concentration of C are so large that they don't change during the course of the reaction, right? And we have no problem observing it. So make it pseudo O, pseudo N, and to figure out O, we just make it pseudo O. Does that make sense? And so A and C are high, are fairly constant. And then here we'd make A and B so large that they're fairly constant. Okay, does that make sense then? And so this is a way to kind of filter out the other stuff so we can see the individual order. And so let's say it came out first order in A, first order in B, first order in C. That would be third order overall. We haven't shown a third order curve, right? But it would be a third order curve. And then we would say, you know, this is how it behaves normally. In a normal reaction, let's say you consume half of A, half of B, and half of C. What happens to the overall reaction? Actually, I forgot. What were the numbers I used for this? Was it 2A? It was 2A plus B plus C yields product. All right, let's say it was, let's say M was 1, N is 1, O is 1. And so the rate law looks like this. The rate is equal to K, A to the first, B to the first, C to the first. And so let's go with this. 2A plus B plus C. If I start off with these all being the same initial, let's go with that. Then let's consume half of A. So I have 1/2 of the initial amount of A. Then B would be what? B wouldn't be cut by 1/2, it'd be cut by 1/4. And C would be 1/4. And so normally if I cut A in half for first order, if I cut the A in half for first order, the rate should be cut in half. In other words, the slope should be half. The positive value of the slope. But what's going to happen here is this. Okay, it's going to be K. Okay, this is going to be 1/2 our original. This would be for A. This would be 1/4 of our original for B. This is to the first power, this is to the first power. And then C, this would be 1/4 of our original for C. And so let's factor out these. This would be 1/2 times 1/4 is 1/8. 1/8 times 1/4 would be 1/32. So we have 1/32 of our original rate. Here's our original rate. It would be 1/32 of our original rate. Even though it's a first order dependence on A, we just cut A in half, but B and C also change, and B and C are also going to slow down the reaction. Does that make sense? And so this is showing the impact. When we let B and C change, of course it's going to have a huge impact on the reaction, because what we're going to observe here is the overall order, right? But we are able to filter out those by doing it pseudo first, and then once we figure it out, then we know how it's going to behave under normal conditions rather than pseudo conditions. All right, today's reaction, we're taking something called crystal violet, which is purple, and then hydroxide, which is colorless, and we're going to form crystal violet hydroxide, which is colorless. This is an easy reaction to follow, because what we can do is we can just look at the purple color disappear and measure that quantitatively. the rate is going to be influenced by the two reactants, crystal violet and hydroxide. So the rate law showing how the rate depends on those will be just given by crystal violet plus to the M, hydroxide to the N. Now what we want to do is we want to figure out the three things. We want to determine what is K, what is M, and what is N. Let me go back 1 second to this. Before I leave this one here, what else do we want to know? Well, we want to know how the slope changes, how the rate changes with concentration. That's given by the rate law. We also want to know one other thing, the other equation which defines that curve. And so it'd start off at a slope like this, but once we're at this point in the reaction, it's gone to 1/32 of our original slope. So it's slowed down pretty fast. So we have the rate law. What's the other equation that we want? Like, for example, I want to know how long it's going to take to get here. How long is this going to take? Is the rate law going to tell us that? No, because the rate is always changing, right? We need the integrated rate law. Here, with these multivariable things, we aren't going to integrate it. We're just going to do single variables, just simple. And so the integrated rate laws that I gave you yesterday are only good for single reactants decomposing into products or pseudo single reactants decomposing into products. Then the integrated rate law is valid, right? Is fine. But even though we know it's first order in A, we can't use the ln of A at time t, over time A at time 0 is equal to minus kt. We can't use that. Why? Because it's not first order overall here. Is that clear? So whenever we have multiple reactants, we aren't going to generate the integrated rate law. You could, if you want to use more advanced calculus, you could do that. You could get it. But we aren't. And I'm not even going to give you the equations for that. And so when we have more than one, we're either going to make it pseudo so we can get it, or we're going to just get the rate law and then that's it. All right, now how can I figure out what M is? Tell me an easy way to figure out what M is. We just make it pseudo M order. And so this, we're going to do pseudo M order. How do I do pseudo M order? I make the hydroxide concentration so big that over the course of the reaction, let's say 90% of the CVs consumed, let's say 90% of the CVs consumed, I want the hydroxide to be barely touched. That means I have to have a huge hydroxide concentration relative to the CV concentration. And so I'm just going to make the hydroxide concentration very big. All right, that's what we're going to do in today's experiment. We're going to make the hydroxide concentration very big. It's already made very big by the stockroom, fortunately, so you don't have to make it. You're just going to use it as is.
To find M.
What?
To find M.
To find M. And so when we do this reaction, then what we're going to do is we're going to watch the crystal violet. But the thing is, we aren't going to watch it with our, visually. We're going to use a spectrometer to measure it. And so the crystal violet has this is what we call the visible spectrum. And in the visible spectrum, we have something on the y-axis called absorbance. How much of the light it absorbs. And then on the, actually, let's go, do I want to go this way? Yeah, let's go this way. I can't remember our spectrometers, if it's this way or that way. Tell me the visible spectrum in terms of colors. Yeah, Roy G. Where does Roy start? Where does R start around?
For your hands.
Yeah, 760. So that's Roy, red, and then violet ends at
370.
390.
390.
This is what are the units for this? Nanometers. So, if something looks purple, why does it look purple? Okay, maybe it reflects purple, or it doesn't absorb purple. If it doesn't absorb purple, we'll call indigo violet purple. How about that? Indigo violet purple. And so the absorption spectrum might look like this, where it absorbs all the other colors except for purple, and it lets purple pass through. And so pretty much it just filters out the other colors, and all you see is purple, right? That's one possibility. Is there another possibility? Yeah, another way we could do it is absorb certain colors, and so that the colors that pass through add up to form purple. And so the easiest one is, if it's not a mix, the easiest one is like this. And so we have the color wheel. Indigo violet will keep together. And so if we look at the artist color wheel like this, and we absorb this color, yellow, then the other colors will mix to form purple. Are you guys familiar with this? From Chem 1A? I talked about this with red food color. Red food color absorbed green. Around green appeared red. So this is one possibility. So what would the absorption spectrum look like here? If we absorb yellow, then the other colors add up to form purple. And this is called the complementary color. Complementary color. There's other ways to do that. You know, we could take different colors out and have the remaining colors add up to purple. And so there are other ways, etc., to generate purple. What taking the visible spectrum will do is it'll allow us to see how the purple color is generated. All right, so let's first do that. Let's check out the equipment, and then we're going to just take the visible